All right, so I will get started. Is there any, I can, whichever one you want me to talk about, I can talk about how to solve if you want. So is there one you want me to go through, or it's all fine? So your mistakes were understandable. I will post a solution, so you can look at that. Okay. Cool. In that case, we will continue with factoring. All right, example 1. Suppose we've got 13x cubed, 20, section 4.2. Yeah, probably. Definitely in chapter 4. Yeah, 4.2. Thank you for asking. Understood. Yeah, and although I will freely admit what I'm currently doing might not be an example that you'd find in the homework. Like this, what I'm currently doing might well be a, well, 4.3 they call introduction to factoring, so maybe this is a 4.3 problem. It's debatable. I don't exactly see the problem I'm doing in 4.3 either. Maybe it's a 4.4 problem. Maybe it's a 4.5 problem. Well. Well, maybe your book is just missing this kind of problem. Well, I finally found some on page 334 that kind of sort of look like the one I'm doing. So I think eventually they want you to be able to do these, but I don't know. I mean, there's nothing stopping us from doing these right now. Now this one, I'm not quite done here. I was going to write x squared, yeah? Okay, so let's talk about how to factor this. And then I will behave. I'll go back and cover the section 4.2 stuff. Okay, but all right, so here we go. So 26 is 13 times 2, right? So what we're looking at is 13 times x. So we could write it this way, right? This is 13x squared times x, right? Plus 2 times 13x squared, right? My point is that there's a common 13x squared in both of those terms, so we can factor it out. So that's how factoring works. We have to find a common thing for both of the terms which are added, and then we can factor that out using the distributive property. So this is 13x squared times x plus 2, and there you go. So maybe these problems are in your textbook, just like glancing through, I can't find which section they're in. They really should be. This is not an unreasonable question to ask you guys. Yeah, they're in there somewhere. I'm just not seeing them at the moment. Okay, so it's just a warm-up example. So let's talk about special forms. So one of the special forms is a plus b squared. So that's a plus b times a plus b, right? So what is that? A times a, right? Plus a times b, plus b times a, plus b times b. Just FOIL it, whatever you want to call that, right? But what is that? Well, a, b, and ba are the same, right? Because a and b commute, assuming they're numbers. So what we have here is a squared plus 2ab plus b squared, right? So this is one of our special formulas. We have a plus b squared is a squared plus 2ab plus b squared. So that's a nice pattern to know about, okay? But one that I use far more than that is the difference of squares. So if I have a squared minus b squared, well, I can factor that as a minus b times a plus b, right? Now, you'd be like, wait, how do you know that? Well, just multiply it out, right? We get what? A times a is a squared. And then we get plus ab, but we also get minus ba. But ab minus ba is 0. And then we still get the b times minus b term, which is give me minus b squared. So this we refer to as difference of squares. Difference of squares. So anytime you have difference of squares, you're pretty much, you've got a way to factor things, right? Like you can see things as difference of squares, then we can factor. If we can see something having this form up here, we can factor. So let's look at a couple examples which exploit these formulas for factoring, right? Example 2. I'll do it over here. Example 2. We could have, say, I don't know, x squared plus 6x plus 9. How does that factor? Mm-hmm. I like that. So you're going back to that, huh? I mean, it's fine, no problem. But you can see pretty easily that that's going to do plus 3 and plus 3, right? And the reason I say that is what this is it's got the pattern. See, 9 is 3. So this is x squared plus 2 times 3x, right? 2 times 3x plus 3 squared. So if I look at that, I can go, wait a minute, that's this pattern, you know? That's this pattern. So that's really x plus 3 squared, right? This is. So there's that one. Example 3. We could have, I don't know, x squared minus 9. So if we look at that, that's really x squared minus 3 squared, right? So what is it? It's a difference of squares. So I can use the difference of squares identity just to factor. That's x minus 3 times x plus 3. And there it goes. Now, of course, you can also fall back on your, I write out my x and fill in the numbers game, right? We can do that, sure. But we don't even have to. And once you see difference of squares, you should be able to finish it without thinking, right? That's the point. Let's do it. Oh, with the x's? It won't let you put the answer as x plus 3 quantity squared? Yeah. Oh. Huh. Well, x plus 3 squared is completely factored. So if the homework is really not allowing that as an answer, it's wrong. But anyway, let's work some more. All right. So I will freely admit, I don't tend to use this one that much. This one comes up way, way more for me. Here's one that'll trip students up sometimes. So how would we factor that? I mean, so my point to you, here's the thing, is you have to look at this. You say, well, that's not a difference of squares. 10 is not a square. See, but 10 is a square. We just have to use our imagination a bit. See, this is 10 minus the square root of 10 squared. So this is a trick. Any number can be replaced by the square root of the number squared, provided that number is positive. And then, see, it's the difference of squares, so I can factor it. X minus the square root of 10 times x plus the square root of 10. When I put this problem on the test, there is a number of students who just go, oh, you can't do it, because they only think in whole numbers. Yeah? But there is more to life than whole numbers, right? Here's another one. X squared minus 81 over 49. So we got to look at, is 81 over 49, what is that? Well, 81 is 9 squared, right? (49) is 7 squared, right? So 81 over 49 is 9/7 squared, right? And so this is equal to x minus 9/7 times x plus 9/7. Does that seem reasonable? Okay. Yeah. Now, of course, it's also, you could also say that this is, I mean, if you want, you can calculate the square root of 81 over 49, you can stick it in your calculator, and what you'll get is 9/7, right? Assuming you have a Casio 1FX 115 and not a Texas Instruments useless. What does it say, Texas or say Casio? There's hope. What'd you get? Square root of 81 over 49. 9/7, right? So I'm just saying if you can recognize it without the calculator, then you don't need the calculator. But of course, you can use a calculator. Here's another one. What if we have 9x squared minus 16? See, this one, let me just point out, we should look at this as quantity 3x squared, right, minus 4 squared. Woo-hoo. And then there were 2. I'll give you a check. Check. And next, I will give you your test. There you go. There was some stuff on the back page there. I stapled it back, so I'm not sure if that was me or you, but anyway, that's why I folded it back over. There was some on there. I don't know. Anyway, So we're factoring at the moment. I had a time for questions about the test to start a class, but we're past that now. But I will post the solution to test 2 in course content here sometime soon. And so you can look at it. And if you got questions about the test, you can ask me next class too. It's fine. Sound good? So, of course, you can also come to office hours and talk to me about it if you want, whatever. It's all good. So right now we're using difference of squares. So the difference of squares is a squared minus b squared is a minus b times a plus b. And we can exploit this formula to do there are many examples which allow us to do this, that allow us to factor using this formula, right? Like this one here. What do we got? So we get 3x minus 4, 3x plus 4, right? So there's that. All right, I think, I don't know about you, but I'm starting to get bored of these examples. Let's move on to the next kind of example, yeah? Well, there's one sort of like slightly more exotic version of this, which I'll talk about since we're on this topic. We could look at something like, I don't know, x to the 4th minus 256. So here you got to use your imagination a little bit more. What's the square root of 256? 16, aha. So this is x squared minus 16 squared. See that? So we can still use the difference of squares formula here. Just now we're using it on x squared being a and on 16 being b. So what do we get? We get x squared minus 16, x squared plus 16. Now, x squared plus 16, game over. That's all we can do. There's no way to break that down further. When you have x squared plus a number, like you cannot factor unless you've got complex numbers to work with. All right? And we don't have those yet. So, but x squared minus 16, what's that? That's x squared minus 4 squared, right? See, this is just, if you allow me to make a little change here, 4 squared, right? So that is x minus 4, x plus 4, x squared plus 16, and there you have it. That's how that one goes. So this example is kind of neat. We get to use the difference of squares formula not once but twice to factor. So there's that one. All right, so let's go back to the kind of plain Jane, ones with the put the x in the x kind of template, whatever you want to call that, those kind of examples, all right? Let's go back to those. So let's call this factoring via guessing, because that's really what we're doing. To be more accurate, it's educated guessing, right? But it's essentially guessing. So this is example 8, right? So here we go. X squared minus 10x plus 16. Factor that. Okay, so so you say I make my template, right? I put my x's. Then what do I do there? What do you think? what should we be thinking? We should be thinking about how we factor 16, right? You got 8 and 2, you got 4 and 4, you got 1 and 16, right? Ooh, I think 8 and 2 might be a winner here because we got 10, right? 8 plus 2 is 10. We've got to have it negative, so what do we do? We do x minus 2, x minus 8, right? So, and then the ultimate judge of whether or not this is right, multiply it out, right? X times x squared, great. Minus 2 times minus 8, 16, good. And then we get a minus 2x and a minus 8x from multiplying that out, right? Minus 2 minus 8, minus 10. Good. So again, the internal logic here was I was thinking about possible ways to get 16, right? It's 1 times 16. It's 2 times 8, right? It's 4 times 4. Those are ways I can multiply numbers to get 16. But then, of course, I could also do minuses of those, right, to still get 16. So there's kind of 6 natural, easy things to think about here. And since we got the 10, it forces us to look at the 2 and 8 possibility, right? And then the minus because we got a minus 10. All right. How about this next one? So the next one, what I do when I've got a 2 like this, I factor it out. So this is x squared plus 3x plus 2, right? Because I prefer not to think about 2x squared if I can help it. And now, see, I've got a pattern, right? And I'm trying to get 2 in the constant term, right? See this 2 here? So that means 1 and, I can do 1 and 2, or I could do minus 1 and minus 2, right? So which one, what do I do? 1 and 2, so plus 1, plus 2. Great. All right, are we good? Okay. Example 10. Oh, I don't know. X squared plus 4x plus 5. Example 11. X squared plus 5x plus 4. I mean, if you can solve example 10, you ought to be able to solve example 11, right? It's the same problem, just 4 and 5 flipped around. These can't be that different, can they? You're like, sounds like a trap. So I'll do 11 first. 4 is what? 2 times 2. I like that. 2 times 2. 1 times 4, right? Or you could do minus 2 times minus 2, or minus 1 times minus 4, yeah? Those are possible those possible ways of factoring 4. I think we should go with 1 and 4, right? Because 1 plus 4 is 5, so we do x plus 1, x plus 4, right? Now 5. Yeah, so we're either going to try x plus 1 plus 5, right? Or what's the other possibility? Those are our potential factorings, right? Does it work? I say, does that work, though? It does not work, right? Because this is literally x squared plus 6x plus 5. And this one, when you multiply it out, is x squared minus 6x plus 5. As you can clearly see, manifestly see, this is not that. That is not that. Our template method has failed. Now then you can ask the question, well, maybe it's that square root stuff we were doing, right? Because it wasn't long ago we had this example. Like here's example 12. I'll do another one. So what if you had, x. Yeah, the question is there any way to factor that? But that would be, okay, so now I agree with you, but x squared plus 4x minus 5 is a different problem. So you said x plus 4, x plus 5? Right, so that one is how you factor this one. Plus 5x minus x gives me 4x. But there's a big difference between this one and that one, which is that this is plus 5, this is minus 5. So that is how to factor this one, but it doesn't help us here. Example 10? Example 10 to us at the moment is a mystery. It shows that there is a kink in our armor. How do we know? The answer actually is, in fact, that it cannot be factored over the real numbers. Well, and let me show you why. I'll show you why. So here's why. So, like a fundamental truth for us. If you have x squared plus something, right? Let's just think about it this way. X squared plus 1 cannot be factored. Over the reals. All right. So, but this is the more general thing is if we have something squared plus something else, it can't be factored, right? Now, so this is a trick, but this can be rewritten as x plus 2 squared. What is x plus 2 squared? Yeah, x squared plus 4x plus 4, right? When we square this out, we get that. By that formula, I don't use too much. Is that fair? Is that equal? It's not equal, right? Because you got 5 over here. This only gets 4, so we have to add 1. So this, right, is equal to that. That, in your face, cannot be factored. It's a sum of squares. Sum of squares cannot be factored. Over the real numbers. So then you're going to ask the question, so how do you know when a given problem can be rewritten as a sum of squares, right? So the simple answer to your question is, be where you are, do what you're doing. You're doing the homework in this book, in the home, and so like, they're going to all be they're all going to be factorable, right? Because they're book problems, so they're all going to work out nice and pretty. This problem, they don't always? No? They throw a curve in there? Well, there's a chance that that's just a mistake in the book. Undefined? Yeah, see, well, see here. So as I'm looking for, let me just take a second here to look through section 4.3. Looking at their examples. Example 1, it factors. Example 2, it factors. Example 3, it factors. 5, 6, factor. Let's see here. Oh yeah, 6 is silly. They just factor out a -2. Sometimes they just factor a number out in these examples. Okay, they do have some factoring by grouping in here where okay, so let me try to explain a difference here. So I'm concerned with the question of when can you keep factoring and when can't you keep factoring, right? Like that example I had with the x to the 4th problem, like this one here. So I'll revisit it. This is example 13. So if I had x to the fourth, let's say minus 9, right? That is x squared minus 3 times x squared plus 3, right? I've factored this, right? So this is factored. I factored, but it's not completely factored. Why is it not completely factored? Because this x squared plus 3, that's a sum of squares. It's a square plus a positive thing. 3 is a square in the sense that 3 is equal to the square root of 3 squared. So this is a sum of squares. Something squared plus a positive thing. That cannot be, you can't break it down. It is what it is. But x squared minus 3, well, that we could factor. That is x minus the square root of 3 times x plus the square root of 3 times x squared plus 3. This, now, that is completely factored. You cannot break that down further. Those are like atoms. They can't be divided. That didn't work out too well, did it? Like calling an atom, it's a basic unit of matter. It can't be divided, right? The word atomic. I mean, physics has since then divided atoms into like the neutron and electrons and the nucleus and the electrons, right? And then they further divided neutrons into quarks and junk. It's like that word atomics turned out not to work so well, but these are atomic. You know, you cannot break these down further. So section 4.3, they're sometimes just like doing part of a factoring, all right? So let's look at some of those. I've not answered your question, though. How do we know when this happens? All right? How do you know that? I don't think your book actually explains. Your book just judiciously works problems which do work, and they ignore the larger question of how do you know when this will work? There's actually an answer. What's that? When it don't work, but sometimes that could just be a lack of skill, right? Or maybe you just don't see the number. Because the numbers can get uglier, guys. They can get a lot uglier. Check this out. So let me show you how we can work backwards to something much uglier. Suppose you had x minus 2 plus the square root of 13, x minus 2 plus minus the square root of 13. Multiply that out, what do you get? We get x squared, right? Minus, well, let's say plus minus 2 plus the square root of 13x plus x times minus 2 minus the square root of 13 plus minus 2 plus the square root of 13 minus 2 minus the square root of 13. It's kind of a mess, right? But what does that work out to? Don't give up. You can do it. Look. So some things cancel here. See, this gives us a 13 times x, right? But there's also a minus 13 times x. So these guys just cancel, basically, right? Whereas I've got minus 2x, minus 2x. So I've got x squared minus 4x. That's from this and that, 4x, right? This over here actually works out nicely. See, this is actually 4 minus 2 root 13 plus 2 root 13 minus the square root of 13 squared. In other words, this whole mess, these guys cancel, and you're just left with 4 minus 13. In other words, minus 9. And so what we're looking at here is x squared minus 4x minus 9. Let me rewrite that again. X squared minus 4x minus 9. If I asked you to factor this with guessing, how would it go for you? Right? So you try guess. You start trying to factor this, right? You don't know. It looks innocent enough, right? It's got an x. It's got a 4 and a 9. 4 and 9, those aren't ugly numbers. They're ugly? Oh, well, that's only because you see what's up here. But if I just started with this, you wouldn't have suspected it. Right? Yeah, 1 and 9 and 3 and 3. Right. Exactly. So, but they have to be minuses, like -1 and 9, or -3 and 3, or 1 and -9, right? Or, yeah. So the thought that -9, well, -9, it's obviously equal to 2, it's obviously equal to the square root of 13 minus 2 times this, minus 2, God, grief, minus 2 minus the square root of 13 times -2 plus the square root of 13. Like, everybody knows that -9 can be written as a product of that number and that number, right? No, right? All right, so is there a hope? Is there a method? Is there a method for factoring which doesn't require guessing? Is there a method for factoring? And so I'm specifically talking about quadratics, okay? What's a quadratic polynomial? So I'm going to show you how we can take the guessing out of factoring. This is an algorithm. Check it out. 2-factor, my thumb hurts, son of a gun, x squared plus bx plus c, all right? Step number 1, write x squared plus bx plus c equals to x plus b divided by 2 squared minus b squared over 4 plus c. So you take half of the coefficient of x and you add it to x, you square that. And then you subtract the square of whatever. You subtract the square of whatever's here over there. Right? Step number 2. If c minus b squared over 4 is greater than 0, you're done. It ain't possible. Over the reals. Because if that c minus b squared over 4 is positive, that means you're looking at sum of squares, you're done. 3, else c squared minus b squared over 4 is less than 0 or equal to 0. Well, else you can do this. Let me just write it. Else you can write x squared plus bx plus c is equal to x minus x plus, good grief, x plus b over 2 squared minus the square root of c minus b squared over 4. I did that wrong. Sorry. B squared over 4 minus c quantity squared. Listen, like, I'm writing the general algorithm here, but this is actually much easier when you do it for examples. So, example. So we looked at x squared plus 4x plus 5, right? So what we're going to do is we're going to take half of 4. Half of 4 is 2, right? So I do x plus 2 squared. All right? Then I subtract 2 squared. And I still add the 5, right? So what is that? That's x plus 2 quantity squared plus 1, which is what I wrote earlier by hocus pocus. Now I'm telling you this is from this algorithm that I know. Step 1, 2, 3. Okay? And that's it. And so I know I'm done. I can't go further. It's a sum of squares. That cannot be factored. Game over. Example 17, though. What was that one we just worked out? X squared minus 4x. No, plus 4x or minus 4x? I can't remember. You guys help me out. Which is the one that I just did and erased? Was it? Okay, this one. So let's go through the algorithm. So we do x minus 2 quantity squared, right? And then I do what? I have to subtract 4, right? So minus 2 squared. And so it's actually minus some minus 2 squared, but that's the same, you know? So what we got then is we've got x minus 2 squared minus 13. That, my friends, is the difference of squares. You just need to use your imagination. 13, you don't have one. Well, I'm trying to help you. So this is square root of 13 squared, right? Lo and behold, what we have is the difference of squares. This is a squared minus b squared, with a equals to x minus 2 and b equals to the square root of 13. So what are we doing? We've got x minus 2 minus the square root of 13, x minus 2 plus the square root of 13. This is 4 minus 9. It's minus 13. That's that, yeah. Listen, I know that you're more comfortable with guessing because you've done it before, right? Do you see, though? I mean, I'm going to show you a bunch more of these next time probably, but because we're just a little short on time at the moment. But look, my point to you is I didn't have to guess. Do you understand that? Like there's no right. So my point to you is there's no guessing here. Like it's mechanical. I take half of that thing. I take x plus that half thing. I square. I subtract the square of whatever number here, and I just keep the plus c. There's no guessing in there. That's arithmetic. And then there are two cases. It's either sum of squares or it's a difference of squares. And if it's a difference of squares, we can fall back on the difference of squares formula, and then this always factors. There's no guessing. This is not commonly taught. People are afraid of this because this is the dreaded completing the square. So now you might ask, why is this called completing the square? Right? I'll try to show you guys that next time, actually. So anyway, thank you for your attention. See you guys Friday. You know, as long as there's not a tornado or hurricane or, well, who knows? Around here, it could be a blizzard.